let's play a game called the CHSH Game. This game has 2 cooperating players and a referee. Throughout the game, the players are not allowed to communicate. We can make sure of that by putting them far away from each other. The game is very simple. The referee sends the players 2 random bits. Each player sees one of these bits and replies with a bit. The winning conditions are as follows. If both inputs are 0, the player's replies must be equal. If the inputs are 0 and 1 or 1 and 0, then again, the replies must be equal. But if both inputs are 1, the player's replies must be unequal. Now let's play. We'll start with a very simple strategy which we'll call the 0 strategy. The players reply with 0 no matter what bit they receive. Let's run the 4 possible input combinations and see in how many of them they win. The referee sent 2 zeros, and the players replied with equal bits, so they win in this case. The same happens when the referee sends out 0, 1 and 1, 0. The players win. But if it sends 1, 1, the players lose. They should have replied with unequal bits. So with this simple strategy, they win with probability of 75%. To recap, the referee chooses the bits it sends randomly. Each player only sees the 1 bit it receives. They can coordinate in advance anything they want, but during the game they cannot communicate. And their replies must be equal or unequal according to this table. Next, we'll analyze what's the best they can do. Here's another example. Now the top player will play a different strategy that we'll call A. It always sends back the bit it receives. The bottom player will play the 0 strategy, same as before. Let's run the 4 possible input combinations again. So far, so good. They won this round too. Here, the top player sent back the bit it received, and the bottom player sent 0. But they should have sent equal bits in this case, so they lost. Here again, the top player sent back the bit it received, and the bottom player always sends 0. But in this case, unequal bits is the correct response, and they won. So again, they failed on 1 input pair. Can we do better? The top player has 2 more simple strategies. Send back the opposite of what it receives, or always send back 1. The bottom player has similar 4 simple strategies. It's easy to validate no combination of these strategies succeeds more than 75% of the time. Each of them fails on at least 1 input pair. But these are all deterministic strategies. Let's try a probabilistic example. These dice are labeled with deterministic strategies. In each game, they toss the dice and play the chosen strategies. So in this game, both of them play the 1 strategy. In the next game, they toss again. And now they play the A0 combination. But we already know that each such combination of deterministic strategies fails for at least 1 input pair. So no matter what comes out, there's a 25% chance that the referee will send this particular pair that makes them fail. Therefore, the maximal winning probability when using such dice is still just 75%. The most general way to describe a player's behavior is using a probability table, such as this one. It shows the probability distribution of the 2 possible outputs given that the input is 0, and the distribution given that the input is 1. This player only sees A, so its behavior can't be affected by the other input bit. This table can represent the deterministic strategies we saw. For example, here is the 0 strategy, where the player always responds with 0. And here is the strategy we called A, where the player sends back the bit it receives. But can such a table do more? The player can implement this table using 2 biased coins, 1 for each row. The red coin has a 75% chance of landing 0, and the green coin has a 40% chance of landing 0. In accordance with the table. When the input bit is 0, the player will toss the red coin and send back the result. When the input bit is 1, it will toss the green coin. An equivalent behavior is to toss both coins in advance before the game begins. The player now has both coins with their results ready. When the input bit arrives, it only needs to pick the appropriate coin. For example, if the input bit is 1, it will send back the result of the green coin. But this reveals the limitation of this approach. If both coins land 0, then the player will reply with 0 for any input. This is the 0 strategy. If they land 0, 1, the player will reply with the same value as the input it receives. This is the A strategy. So all these coins do is randomly select deterministic strategies with some probabilities. We can design a die that selects these strategies with the same probability distribution as the coins. And we've already shown that with dice, the players can win at most 75% of the time. So it seems there's nothing we can do to get better performance. But now let's give the players entangled particles and see what happens. These boxes measure quantum spin, so we'll discuss this topic next. Let's start with the classical particle. Its spin can be characterized by an arrow defining the axis of rotation. The spin can point in various directions. If it points in the opposite direction, it means that the rotation is along the same axis but in the other direction. Now let's discuss spin in quantum physics. It's going to be a bit confusing at first, but bear with us. For our purposes, the rules are going to be fairly simple, and we'll explain and demonstrate them several times. Here is our particle. It is an elementary particle similar to an electron. We can use this device to measure its spin, but we need to choose a direction first. There are always only two possible outcomes. Either we find the spin is pointing up along our axis. We'll call this result 1. Or pointing down. We'll call this result 0. Let's assume the 1 option occurred. If we repeat the measurement at the same angle, we'll always get the same result. But if we measure the spin along another axis, then again there are the same two possible outcomes. 1 for spin pointing up relative to our measurement direction, and 0 for down. The measurement also changed the state of the particle, so now if we return to the previous direction, again we'll get two possible outcomes. And here's a simple probabilistic rule. Say the current particle spin is as shown here. Now let's rotate our device by an angle of theta. When we make a measurement, we'll get the two possible outcomes, and their probabilities are given by these formulas. Let's see what it means for various values of theta. If theta is 0, then the cosine is 1. This means there is a 100% probability for getting 1. For 45 degrees, we get about 85% for 1 and 15% for 0. For 90 degrees, it's 50-50. For 135 degrees, it's 85% for 0. And for 180 degrees, it's 100% will obtain a 0 result. Now let's choose an angle and make a measurement. We're most likely to get 1 here. After the measurement, the state of the particle changes. The spin is now along our new axis. Now the same probabilistic rule applies again, relative to the new arrow direction. Let's demonstrate this with an experiment. Here are 10 particles, all having the same state. We can confirm that by performing measurement at the same angle as the arrow. Now let's measure at 45 degrees relative to the arrow. According to the cosine formula, we expect about 85% to come out 1, an arrow pointing up relative to the measurement direction. Intuitively, it's because the current spin is already close to the up direction. For simplicity, let's replace those that came out flipped, so they'll all be in the same state again. Now we'll measure at 90 degrees relative to the arrow's direction. We expect a distribution of 50-50. Again, let's replace some of them. Finally, let's measure at 135 degrees. We now expect only about 15% will result with 1. Again, intuitively, the arrow is likely to remain close to where it is now, so it is likely to point down. The particle can also be in this state. Here we have no knowledge about the particle's spin in any direction on our measurement plane. It is common to interpret this state as the spin being undefined and not just unknown. We'll stick to this interpretation. Later, we'll discuss whether there are alternatives. If we make a measurement, there's equal probability for each outcome in any direction we choose to measure. After the measurement, we return to a state where the spin along one axis is defined, and from here we have the same rule we saw before. Two particles can be prepared in a special way. For both of them, the direction of the spin is undefined. But one thing is defined: they have opposite spins. This is quantum entanglement. We can now separate them, move them far away from each other, and place them in boxes. The entanglement still remains. Let's measure the top box. Since the particle's spin direction is undefined, there are equal probabilities for each outcome, like we saw before. Let's say we'll get 1. Our particle state has changed, but the strange thing is that the bottom particle state has changed as well, in what's sometimes called spooky action at a distance. Since it was defined that they have opposite spins, the bottom particle now has its spin defined as well, on the same axis we chose for the top box, but in the opposite direction. This change happened instantly, even though it is far away. Also, the entanglement broke, and from here on the usual rule applies. For example, if we measure the bottom box at an opposite angle, we'll get 1 for sure. Let's exercise a bit. We'll measure first the top box. Now we'll measure the bottom box at an opposite angle. All the pairs came out equal. Now we'll measure both of them at the same angle. They all came out unequal. Next, we'll measure them with a difference of 135 degrees between the two devices. We are now likely to get the same value in the bottom box as well. To see why, let's sort the pairs. And look first at the left side. We measure the bottom box at 45 degrees from the current arrow. This means we'll obtain 1 with probability of 85%. On the right, we measure at 135 degrees from the current arrow, so we'll obtain 0 with probability of 85%. Either way, in 85% of the pairs, we get equal bits. We can similarly analyze any other case. And here's a summary showing the probability distribution of the 4 possible outcomes. This distribution is only influenced by the difference between the angles of the two devices. Let's set them to opposite angles. There is a 50% chance for 2 zeros and 50% chance for 2 ones, so there's a 100% chance we'll get 2 equal bits. Now let's change to a difference of 135 degrees. There's still a high probability of getting equal bits, about 85%. At 90 degrees, there's equal probability for each of the 4 outcomes. At 45 degrees, there's about 85% chance for getting 2 different bits. And if we measure at equal angles, we'll get different bits for sure. Let's get back to the CHSH game. We are now ready to present a very simple quantum strategy. Here's a simple strategy. The players will choose the measurement angle based on the bit they receive. We marked these angles on the dial. Let's see how this works. If the referee sends out 2 zeros, both players will set their angles at the notches marked 0. The angles are close to being opposite. They are 135 degrees apart. They'll get equal bits with probability of about 85%. Recall that according to our rules, this means they win in this case. The same thing happens when the referee sends 0-1. The bottom player adjusted its angle to the notch marked 1, but the angles are still 135 degrees apart, and again the players have an 85% chance of winning. The same is also true for 1-0. When the referee sends 1-1, the players will set their angles close to one another. They are now only 45 degrees apart. This means they'll get unequal bits with probability of 85% and win again. Therefore, for any input combination, they win with probability of 85%, 10% higher than the maximum allowed by classical physics. Let's simulate a few games. We'll count in how many of them they win and their average success rate. For each game, they get a new pair of entangled particles. Such experiments were conducted in real life. After many games, it becomes apparent the players have broken through the 75% barrier. Of course, in real life, we can't see what's inside these boxes. We can only theorize. Perhaps the way we described things so far is completely wrong, but the players are winning more than we initially thought possible. We'll spend the rest of the video discussing what this means. Previously, we said the spin is sometimes undefined. We stressed that it's not just unknown to us, the particle simply doesn't have this information. Let's try now a different interpretation. We'll assume the particle's state does have all the information. These arrows determine in advance the result of each measurement along any direction we can choose. For example, if we measure at this angle, we'll get 1. Also at this angle. At this angle, we'll get 0. This is an example of a hidden variable theory. We may think the particles behave randomly, but that's just because we can't see their hidden state. We'll further assume there's no spooky action at a distance. When we measure one particle, the state of the other particle will remain the same. So we've made two assumptions. Measurements are deterministic and no spooky action at a distance. Together, they are sometimes called local realism. We use it here in this sense, though note it's sometimes used with other meanings. Now let's give the players two particles of this type and try our quantum strategy. Let's focus on the top player. If it measures at the notch marked 0, it will deterministically get a 0 result. Also at the notch marked 1. So this particle basically tells it to play the deterministic 0 strategy. The bottom player also gets 0 at both measurement angles. So both players play the 0 strategy. We know it fails when the referee sends 1-1. So they can only win 75% of the time. But the same is true for any pair of such particles. Since measurements are deterministic, each particle prescribes some deterministic strategy. And each such combination fails for at least one input pair. So with local realism, the maximal probability is 75%. By reaching 85%, we have proved quantum physics is not locally realistic. And since these experiments were done in real life, nature is not locally realistic either. We have disproved the combination of these two assumptions together. It's still possible that only one of them is false. We'll reveal which one later. But now let's turn our attention to the rule that the players can't communicate. Here is our game again, but this time we gave the players a magical device. Each box has a handle that can be in the 0 or 1 state. Each box also has a screen. The bottom screen always shows 0. The top screen switches to 1 only if both handles are set to 1, like an AND gate. With this device, the players can win 100% of the time. Let's watch. But there's one problem with this device. It's a signaling device. When the top handle is in the 1 state, the top screen shows the state of the bottom handle. This allows the bottom player to communicate the bit it receives to the top player, and obviously this wins the game. According to special relativity, signals cannot travel faster than the speed of light. This magical device passes the signal instantly. If such a device existed, it would have caused a serious disruption to cause and effect relations. So we have good reasons to believe it can't exist. But here's a workaround. This new magical device is very similar to the previous one. Inside each box, there's a coin. The two coins are magically locked to be in the same state. The handles don't change that, except when both are set to 1. Then the top coin flips. But the players can't observe the coins directly. To get a reading, they must activate the boxes. This first rotates both coins a random but equal number of times, and the results appear on the screens. So the players get random equal bits, or if both handles are set to 1, they get random unequal bits. With this device too, they always win. Let's see a few examples. Now let's focus on the top player. All it sees is the result of a random coin toss. The bottom player has no control over which value it will be, and therefore cannot use it to send information. And yet, the player's replies are perfectly correlated according to the rules of our game. Such correlations are called non-signaling correlations. Because this device is non-signaling, we have no strong reasons to reject its existence. And a similar device does exist, the quantum device we showed before. It behaves very similarly, except it's a bit noisy. It has handles that can be in the 0 or 1 state. And let's recall the outcome distribution. If any of the handles is at 0, the results are likely to be equal. And if both handles are at 1, they are likely to be unequal. To see the non-signaling property, let's hide the bottom box. Note that the distribution of the top result is 50% for 1 and 50% for 0, just like a random coin toss. It remains so no matter what the bottom player does. So the top player can't obtain any information from it. Quantum physics doesn't tap the full power of non-signaling correlations. It can be shown that about 85% is the maximal probability it allows. We previously ruled out the combination of these two assumptions. We'll now repeat this proof more generally with just one assumption. A formal statement of this assumption is called Bell locality. Previously, we saw these locally realistic particles. Each particle prescribes to the player a table that defines its behavior. Since these particles are deterministic, the tables are deterministic too. Now let's assume the particles are intrinsically random. They still may have some hidden state that we cannot see, and this hidden state defines some probability distribution over the possible outcomes. The Bell locality assumption requires that when we measure one particle, the state of the other one will stay the same. And therefore, the table that describes it stays the same too. But we proved in the beginning of this video such tables are equivalent to ordinary dice, and therefore can't win more than 75% of the time. So a score of 85% rules out Bell locality. Finally, let's observe how quantum entanglement violates the Bell locality assumption. Initially, the tables look like this. Now we'll measure the top particle. Its table changed, and that's a local effect, but the other table changed as well. Such non-local effects allow us to break through the 75% barrier.